Hello, we are the B Project, and our advisors are Professor Richard Martin and Dr. Richard Howard. Here you can meet the team. And let's jump into the motivation. So nowadays, there is a lot of radio frequency pollution due to electronics. So any electronics that we own, from cell phones to electric cars to smart fridges, and all these, electronics emit a lot of RF. And we want to determine if there are any possible biological impacts of RF on bees. We're specifically choosing bees because they account for about a third of our crops on Earth. Bees are pollinators, so they play a big role in the food that we eat on a day-to-day basis. Here's our experimental setup. On the left side, you can see that we have an indoor observation beehive. This beehive actually connects to the outdoors, and bees can go in and out, but the physical hive itself is inside of Professor Richard Martin's garage. And there's a black box because bees don't like well-lit environments. They like to stay in dark areas. So we need to put something to block out all the light. And as a result, in order to capture videos with their cameras, we need to use infrared as an illumination source. So that's why there's a reddish tint on that monitor. A closer view of the beehive is on the right side. You can see the comb and a bunch of bees. And importantly, there is a coil in the bottom portion of that image that serves as our stimulus. So that leads me to our objective, which is to use computers and cameras to determine if honeybees can detect the magnetic field, and if so, how do they react to it? Okay. So our first method to figure this out is to use heat maps, which, to be more specific, we want to see where bees are actually moving and concentrating the movement in respect to the magnetic field. So on the left side, that little image that you see over there, it's an image of a heat map, and the brighter lit areas means that there's more movement. And you can see the outline of the coil, which shows that the bees are concentrating the movement around the coil. And this may show that there is some sort of correlation between bee movement and the coil that's emitting the electromagnetic radiation. Another way we can try to find this and meet this objective is to attempt to find orientation of bees. On the right side, you can see that we applied some machine learning algorithms to figure out the orientation of honeybees on this comb. And with those arrows, you can plot the angles of the honeybees in respect to the coil as well. And for the future, we want to improve our results for this. And yeah.
So in addition to that method that Justin was just talking about, we also implemented a background subtraction algorithm onto a video that we took of the bees. So what is background subtraction? So at a very simple level, it takes a pixel that it picks up as moving and turns it white, and otherwise it turns it black. So on this slide, you can see here, everything that's moving, it picks up as white. And then what we did after that was draw ellipses around these white blocks. So how does this help with what we want to do for our project? Well, whatever direction the ellipse is in, as indicated by the angle measurement numbers up there, that tells us the orientation. So we can compare the orientations of the bees when the field, as you can see in the middle of the frame, whether the field is on or off. So we can compare the values. So now on this slide, this represents the difference in values between when the field is on and when the field is off. So here you could see it says negative field on the left and positive field on the right. That just means that those are two separate states of the field. So it's either in a negative state, positive state, or off. They're just two different types of directions of the field. So you can see that the no field on the left and right is in red, and the field is in blue. And the x-axis are the angle measurements, and the y-axis are the total amount of times that that angle shows up over the course of the entire time period of each state of the field. And you can see there's actually very similar angle measurements throughout the entire frame, the entire video. But what's interesting is that in the middle, around 80 to 100 degrees, there are far more frequent occurrences of that than anywhere between 0 and 60 and 120 and 180. So for the future, what we want to try to do is make sure there are no false positives or false negatives in our findings with the ellipses, to make sure we don't catch any, we don't draw any ellipses around things that aren't bees, and that we draw that each static bee, ones that aren't moving, have ellipses drawn around them, because since they aren't moving, the algorithm doesn't see that as a bee. So that's something that we would for sure want to fix in the future.
So another aspect of our work was to develop a computer simulation of the footage from the beehive. This was so the team would be able to test our computer vision algorithms in a controlled environment. This was necessary since the lighting and the resolution of the actual beehive video was still a work in progress, so in the controlled environment, there's no room for error. In the bottom left, I included this pink image of the actual beehive that we were experimenting on. As you can see, it's a little difficult to make out what you're looking at, so it's just as difficult for a computer vision algorithm. The green ovals are supposed to be covering the bees, but some of them aren't, and this is because of the lighting and resolution. And on the right, I included an image of some of the progress we made in the simulation to show the difference between having many variables to deal with in the real video and the controlled environment of the simulation. And the simulation is being developed using Pygame, which is a Python programming language library that is used to easily generate computer graphics.
So over the course of the internship, we were able to create a simulation that had yellow rectangles accurately mimicking the movement of bees. Additionally, we were able to load a bee image into Pygame and get it to buzz like a bee. And we used a background estimation program that Joel was talking about earlier to get a background from the high videos that didn't include the bees. And we were able to use that picture as the background for our simulation. So one of the challenges that we faced is that this process originally developed as two separate programs, but ultimately we had to work to combine the two programs together to get the full simulation with the movement and the images. Additionally, we had some trouble making the bees rotate to match their direction of movement, as opposed to the bees moving sideways or backwards. In the future, we would hope to expand the program to include like hundreds of bees in order to accurately represent a real life beehive. And then we would want to start incorporating the tasks that bees perform, such as comb construction, feeding, etc.
Yep. And lastly, we included a video of the actual beehive on the left versus this as far as we came with the simulation on the right. And clearly there's still a lot of work to be done to make the simulation as realistic as possible so the computer vision algorithms can be as accurate as possible. So most importantly, we want to add things like real footage and real background, so to recreate the bees' actual behavior.